Okay, so we're going to get Ted fired up here. He's going to tell us a little bit about detecting spatial orientation and using EEG.
Hello everyone, I'm Ted and I'm from School of Interactive Arts and Technology, Simon Fraser University. Today we'll present to you one of my recent work called Detecting Spatial Orientation Demands During Virtual Navigation using EEG Brain Sensing. I'd like to begin by defining what spatial orientation is. It is a natural ability of most animals, including humans, to maintain the body orientation and position in relation to the surrounding at rest and during motion. In our daily life, we rarely get disoriented as we are too familiar with the environment that we are in. However, it might happen when we get to some new places that we haven't been before. For example, an airport that you haven't been before. For some, you just come here, a new town, at a conference, you cannot find the room, then you get disoriented. Apparently, it happens more frequently in VR, not only because the environment is strange to you, but also because there are several factors that might affect our cognitive processes, including spatial orientation. Nowadays, we can easily set up a quite large tracking area, but it's actually not large enough for most VR applications involving navigation. That's why we need some locomotion interface to go beyond the restricted tracking area. We can either use teleportation or we can use some input device to control our translation and rotation like a joystick or a controller. But VR is not only about what we see through the SMD, and spatial orientation is not only about the heading direction, but also about our body direction. So I have an example here where the body direction and the heading direction are not aligned with each other. So if we want to go forward, which direction should the player or should ourselves be translated? Is it the heading direction or the body direction? So in our real life, we usually go toward our body direction because we have an ability to keep going ahead and look at different things. But it doesn't work in VR because most of the locomotion interface will make you translate it and rotate it around your heading direction. There's another issue when you use some locomotion interface, that is the sensory conflict, because sometimes your visual system signal that you are moving or rotating, but the vestibular system signal the opposite because you are not actually do that in the real world. So spatial disorientation become a big issue in VR because it will directly affect the user behavior, performance, engagement, and their whole experience. They cannot fully enjoy the experience when they get tired or disoriented. That's why there's been a large body of research investigating spatial orientation in VR. But how has spatial orientation been assessed in private research? We usually design some simulated tasks that require maintain a good spatial orientation in order to perform the task accurately. But by using those simulated tasks, we make an assumption that people who can maintain a better spatial orientation will perform the task better, and people who perform the task better have a better spatial orientation. It's normally true. However, there are potential confound when we try to assess or evaluate some psychological outcome without assessing the cognitive processes hidden behind. And nowadays we have electroencephalogram or EEG practical brain sensing that we can use in a lot of SCI research, including VR. Nowadays we have lots of consumer-grade BCI that are relatively affordable and easy to use with the supported SDK. EEG allows us to record the neuron oscillation in a wide range of frequency. Previous research has classified them into 5 bands. We have delta, theta, alpha, beta, and gamma. In this research, we specifically interested in the theta band, which is from 4 to 8 Hz, as it is associated with meditation, relaxation, and workload. The correlation between theta band oscillation and the spatial orientation has been investigated in previous study. In 1999, Kahana observed a striking episode of theta oscillation when he asked his participants to explore a virtual maze. And in 2002, Araujo suggests an association between the theta band oscillation and the performance of navigational tasks when he asked his participants to explore a virtual building. And again in 2003, Bishop confirmed again the relation between theta band oscillation and the retrieval and encoding of spatial information. In this study, we aim to build an AI that can observe or monitor your neural activity and detect the spatial orientation demands during the virtual navigation. It's like if you have an antivirus software, it's running in the background of your computer and will notify you when it detects some potential threats to your system. Similarly, we want to build anti-spatial disorientation that can notify user when it detects some potential threats to their spatial orientation. So technically, we use a machine learning technique called CNN, or convolutional neural network. CNN has been widely used in image recognition and image classification problem. We can easily train something like a bird detector by giving it two sets of photos. The first set includes different photo of bird, and the second set includes different thing but no bird. So after the training phase, after we train the network, we will have a bird detector and we can give it a new photo, and it will help you to detect if there is a bird in that photo or not. Similarly, we aim to build a spatial orientation demand detector when it can receive the input bits of EEG data, and it will detect or predict if there is any spatial orientation demand in that data or not. And in order to collect the data, we design a within subject experiment where each participant will experience both conditions, the normal condition and orientation demanding condition. In the normal condition, they were presented to a virtual environment and passively navigated through a multi-segment trajectory. And in the orientation demanding, they have an additional task that at the end of every trajectory, they will have to point back to the origin. In other words, in the orientation demanding, they will have to pay more attention to their movement, position, and orientation. I have a simulation here. For example, this is our participant, and now they will be passively translated on a two-segment trajectory. At the end of the trajectory, they will have to identify in which direction the origin is and point toward that direction. Okay, and this is how the actual task looks like. We intentionally design the environment not to provide any visual cue except the optic flow from the star field. And now let's do the task together. Okay, so make sure that you're heading toward this direction, it's this screen, to make sure that we have the same orientation. And I will start the locomotion. After the translation, please help me to identify in which direction our origin point is, okay?
Oh boy.
Okay, are you ready?
Ready.
1, 2, 3. Okay. Okay, so anyone can help me to identify in which direction our origin point is?
Right behind you.
Yeah, close. Thank you. You have a correct answer. So this is the trajectory that we have visited. So the correct answer is around our 4 o'clock direction. If you're heading this direction, then it's around there. Okay. So in order to validate the detection model, we use cross validation. So all the data was randomly divided into 3 folds. 2 of them were used for training and 1 remaining used for testing. And actually we evaluate in 2 modes. In the intersubject, we try to train separated network for every participant and only use the data from that specific participant to test the relevant network. And in the intra-subject condition, we try to put all the participants together and train only 1 single network and use that for everyone. And the results show that our detection model can predict 63% accurately in the intra-subject condition and significantly higher up to 96% in the inter-subject condition. This result is reasonable as previous research has pointed out that EEG data can be different between individuals even when they are in the same condition. So with this high result, we can confidently say that CNN is robust for detecting spatial orientation demands in the EEG data. For the next step, we will implement the actual software or plugin that other researcher and developer can use to monitor their user orientation during the virtual navigation. In terms of science, this study has provided a more objective approach to assessing spatial orientation in VR. And I have a takeaway message for everyone. That's EEG is a feasible brain sensing to assess spatial orientation in VR. And CNN is a robust technique to detect spatial orientation demand in EEG signal. Thank you for listening.
Wow. Exciting stuff.